Hello, today we're continuing in our series on nuclear physics and we're going to start looking at the shape of the nuclear potential. Now in the last video on neutron-proton scattering we were looking at a nuclear potential that looks something like this. This is the nuclear potential, this is R equals R0, this is minus V0, which for a deuteron, or in other words a neutron-proton potential is minus 36 MeV. For a deuteron that's bound, in other words where the proton and neutron are bound in the deuteron, the binding energy is actually quite small. It's minus 2.225 MeV. But when you're talking about neutron-proton scattering, you're not talking about a deuteron. They're not bound. They are free. And the energy of the neutron is actually a positive energy. It's not a negative energy. It's not bound. It's a free neutron accelerating towards or moving towards a target with protons. And once again you get this kind of two-region concept, the region inside the nuclear potential, the region outside the nuclear potential, and we develop two equations. The wave function inside we said was the familiar A sine kr term, and the wave function outside was E times the sine of Lr plus delta, and delta we said was the phase angle. Just to remind you that K is, from the Schrödinger equation, the square root of 2m E minus V0, where E is this energy of the incident neutron, V0 is the nuclear potential, and that is divided of course by h bar squared, and here L is just the 2me over h bar squared. There's no V term here because in region 2 the V term, the potential, is 0. That all came out of the last video. Now I want to describe some experimental results for neutron-proton scattering. And what we're going to measure is the value of delta, this phase angle, delta. This is the positive and this is negative. And if you look at neutron positive scattering, so you're taking a beam of neutrons, scattering them off of a target that contains protons, you get, and this is energy. So we're measuring energy of the incident neutrons along the bottom, and you get a graph that looks like that. Actually you get several, but I'm only going to plot two. This is S equals 1, this is S equals 0, spin terms. Remember in the last video we showed that the you have to take account both of the S equal 1 terms and the S equals 0 terms to get the total cross section. In fact there are sometimes P terms as well that can be introduced, but I'm just going to leave those two. You'll notice that they cross the line, and that is at about 300 MeV. So at low energy, the phase angle is positive, and at high energy, the phase angle is negative. And really the purpose of this video is to ask the question, why? And what is its significance in terms of the nuclear potential? Well, let's start off by just thinking about this nuclear potential here, which is the one we've been using so far, here, and look at the value of the wave function. So here's the wave function that I'm going to plot. The wave function value is on the y-axis, if you like, and separation r is on the x-axis. And this is r0. That is the point at which we are alleging that the nuclear potential falls off. We are using a square well. Of course, the nuclear potential doesn't fall off quite that sharply, but that's the assumption we're making at the moment. And what I want to do is simply to plot a sine LR wave. Right? That's all I'm going to do, plot a sine LR wave, not the delta, just a sine LR. So here's a sine LR wave that looks something like That's one wavelength of a sine LR wave. Now, of course, the LR wave operates in region 2. So actually, although I've drawn it in region 1, because this is region 1, obviously, less than R0, and region 2 is greater than R0, this bit of it shouldn't actually be there, right? Because that actually isn't, that wave function doesn't exist inside region 1. So in a sense, blot that from your mind. Now, what I want to persuade you is that K is greater than L. Why? Because E minus V naught is E minus a minus term, and the minus is minus 36. So E minus V naught is the equivalent of E plus 36, whereas for L you've only got E. So this term has an E plus 36, this term has an E, so K is greater than L. Are we all agreed? Yes. That means that the wavelength of the K wave will be less than the wavelength of the L wave, because K, which is essentially the wave number, is proportional to 1 over lambda. It's actually 2 pi over lambda, but it's in proportional terms, K is proportional to 1 over lambda. So as K increases, lambda decreases. So if K is greater than L, that means the wavelength of the K wave is less than the wavelength of the L wave. Okay, and what we've plotted is essentially the L wave without the phase difference. So if we plot the K wave, then its wavelength is not going to be as great as the L wave. So it's going to go something like, and then it's going to continue. But of course the K wave only operates over region 1. So I've actually drawn it beyond, and I shouldn't have done. This bit you can also forget. Now the important thing to notice is that at the boundary, at R0, the K wave stops here and the L wave starts here. And that's a discontinuity. And you're not allowed a discontinuity. Remember the rule, the wave function must be continuous. So how can you make that wave function continuous? Well, you need to take this bit of the L wave and you need to take the whole wave and shove it to the left. Right, so the entire wave has to be moved to the left so that this point coincides with this point. The whole thing just moves. This point coincides with this point, then you will have continuity. The wave function will be continuous. So essentially, bodily, the whole of this LR wave must be moved to here, which means it will, having been shunted, it will then follow the dotted line because it's all been moved lock, stock and barrel to the left. And the dotted line, of course, now is the sine LR plus delta wave, because it has been shifted by an amount delta. So when you shift a sine LR wave, you get a sine LR plus delta. What the value of delta is, whether it's positive or negative, we'll find out in a moment. Right? So let's look at where these two waves cross the point where the wave function is 0. I'll call them R2 and R1. R2 is where the sine LR wave crosses the origin. R1 is where the now shifted sine LR plus delta wave crosses the origin. Now, when I say crosses the origin, crosses the line where psi equals 0. When psi equals 0, that means that the sine is going to be equal to 0, which means that the value of the term is going to be equal to pi, because sine of pi is 0. So if we look first of all at the sine LR wave, that means that at R2, the sine of LR2 is 0, which means that LR2 is equal to pi. Okay? If we look at the sine LR plus delta wave, then when R is R1, the sine of LR1 plus delta is 0, because that's where it crosses the line when psi is 0. And that means that LR1 plus delta is equal to pi. And that means that, of course, that LR2 equals LR1 plus delta, which means that delta is equal to LR2 minus LR1, which is L into R2 minus R1. But R2 is greater than R1 because we had to shove the wave to the left. So R2 is always bigger than R1 in these circumstances, which means that this term is positive, which means, of course, that delta is positive. So delta has a positive value in these circumstances. And if we go back up to the experimental result, we're talking about low energy, you will see that delta is positive. So this region where delta is positive, we have explained by virtue of this, as it were, shunting the LR wave to the left so that the wave function is continuous at R0. So in what circumstances could delta ever be negative? Well, let's speculate what happens if, when we plot our nuclear potential, here's V, so far we've always plotted a well, a potential well, an attractive potential well. Suppose we now plot a repulsive term. Instead of it being a well, it's now a barrier. It's now, instead of attractive, it's now repulsive. Here is the value of E, the value of the incident neutron. This is the value V0, the nuclear potential that is now repulsive. And this is some value of R, which I'll call R alpha. It is not necessarily the same as R0, indeed it won't be. But I'm just going to call it R alpha. There's a repulsive term which exists over a region R alpha. And once again, we can think of regions 1 and 2. And once again, the formulae will be exactly the same, falling out of the Schrödinger equation. You're going to get that the wave function in region 1 is A times sine kr, where k is going to be equal to the square root of 2m e minus v naught over h bar squared. And the wave function in region 2, where there is no repulsive term, is going to be E sine LR plus delta, exactly as we had before, where L is just the square root of 2me over h bar squared. There's no v term because in region 2 v is 0. And now what I want to be able to persuade you is that in this case L is greater than k. How can I demonstrate that? Well, E minus V naught is just that gap. There's E, there's V naught, they're both positive. E minus V naught is that small gap between the two. Whereas the value of E is everything from 0 up to E. So 2me is going to be greater than 2m times E minus V naught. L is greater than k. So the wavelength of the L wave is less than the wavelength of the K wave. So let's do what we did before and plot the wave function. There's the wave function against separation. And once again, I'm going to plot just the sine LR, not the delta, just the sine LR wave. Here I'm going to put, this is R alpha. So that's the point at which the wave finishes. And on this occasion, I'm going to kind of put dots like that up to the point where the LR wave starts. And then it's going to look something like that. Okay, so the LR wave, I've plotted in solid form only in the region 2 where it exists. It doesn't actually exist in region 1, but if it did, that's what it would do. Okay, that's the sine LR wave. Now, the wavelength of that wave is less than the wavelength of the K wave, which is the wave which, which is the wave which operates inside the region 1. So that wavelength is going to be greater. So I'm going to go up to, say, there, and then if it continued, it would continue down there with a greater wavelength, okay? So again, at the boundary at R alpha, which is the point at which the repulsive potential ceases, we've got a discontinuity. So once again, we are asking the question, how are we going to accommodate that discontinuity? Well, this K wave, remember this is the K wave, that would continue like this. And if you were to move this point on the L wave to here, then you would have continuity. In other words, if you take this L wave and shove it to the right, so that that point coincides with that point, you've now got a continuous wave. And that means that the L wave, when shunted to the right, will sort of look like this. And that is now the sine LR plus delta wave, because the phase difference by shunting it to the right is delta. And now once again, where it crosses the point where the wave function equals 0, I'm going to call that R1 and I'm going to call that R2. Let's look at the sine LR wave. That's the solid wave. When it crosses the point where psi is 0, that means that sine LR is 0, which means that LR1 equals 0, it equals pi. And when the LR1 is pi, the sine of LR1 is 0, which is what you get here. Here you've got that the sine of LR plus delta is 0 at R2, which means that LR2 plus delta equals pi. Therefore, LR1 equals LR2 plus delta, which means that delta is equal to L into R1 minus R2. But if you observe, R1 is always less than R2 because you had to shove this wave to the right in order to match up the discontinuity. And that means that delta is negative because R1 is less than R2, so this is going to be a negative term. So that explains the, if I can redraw the diagram, if you remember the experimental results for measuring delta at different energies were that you got a graph that looked like that. Crossing the origin, there were in fact two, but I'll just draw one. Crossing this point when delta changes from positive to negative at about 300 MeV. So what is the explanation? Well, the explanation is that at low energies, the neutrons, this is, remember, neutrons bumping into protons in a target and scattering. At low energies, the neutrons are getting into the point where they are experiencing the attractive nuclear potential that we talked about when we drew the square well that looked like that. This is an attractive nuclear potential at low energies. But when you get to high energies, what you're really seeing is that the neutron is butting up against the proton. And if you go to higher energies, potentially the neutron and the proton will kind of start to merge. And nature will not have that. Nature does not want densities being created, infinite densities inside the nucleus. So the trick is to say that at this point, the potential goes the other way. It's now a repulsive potential, which says if you get too close, instead of that nuclear potential being an attractive potential, it's a repulsive potential in order to hold the nucleons slightly apart so they don't crash into one another and so they don't attempt to merge. So that is telling us something about the shape of the nuclear potential. What we are saying is that up to some point R alpha, which is what we had before, the nuclear potential is in fact a repulsive potential. If the separation of the neutron and the proton is less than R alpha, then the nuclear potential will force them apart, not pull them together. That stops them from crashing into one another or even attempting to merge. But once you get to R alpha, the nuclear potential now becomes an attractive potential up to the value of R0, which of course is going to be equal to, well, R total radius is equal to R0, a to the 1/3 is our standard definition for the radius of the nucleus, and that's this value here. And thereafter, it's 0. So our shape is, over the very first small distance, which might be of the order of 0.5 Fermis, if you try to get any closer than 0.5 Fermis apart, nuclear potential becomes repulsive. Between 0.5 and, well, in the case of a neutron or a proton, about 2 Fermis, it's attractive, and thereafter it's 0. In practice, of course, the potential is not quite as square as that. It will look something like this. Here's the repulsive potential. This is the potential. This is separation. The repulsive potential stopping you from, in fact, it probably goes up to infinity, actually, rather than curving off, to stop the proton and the neutron from colliding. Here is where you're going to be able to have an attractive force, and then it tapers off to 0. And what this essentially means is that once you get inside the nuclear potential, let's leave it like this, the protons and the neutrons can be, as it were, evenly spaced. They can't get any closer, because if they attempt to do so, this repulsive force will pull them apart. So you get an even distribution of the protons and the neutrons within the nuclear attractive force, and that is why when you measure nuclear density against distance, you get something like this, where over the broad range of the radius of the nuclear potential, the density is constant, and only at the edges does it taper off. If there were no repulsive term, of course, the nucleons would all be attracted and squash into one another, and you would get essentially an infinite density when the separation was very small. This arrangement with the repulsive potential at very, very small distances means that you can keep a standard constant density throughout the broad range of the nuclear force. So this is giving us some idea about the shape of the nuclear potential.